All right, so the following problem asks to calculate the wavelength in meters of the wave associated with a 1 kilogram mass moving at 0.278 meters per second. So what is this question really asking us for? It's asking us to calculate the wavelength in meters of a wave associated with a 1 kilogram mass moving at the following speed. Well, we're looking for wavelength of a moving object. Well, we know the de Broglie wavelength, so wavelength is equal to Planck's constant divided by the momentum object, which momentum is equal to your mass times the speed in which it is moving. So we have the equation that we're utilizing, the de Broglie equation, because when we know that Einstein had stated that light can act as both a wave and as a particle. Early on, we used the equation that correspond the wave-like properties of light. The speed of light is equal to wavelength times frequency, and we also could calculate the energy that was associated to it. But the particle properties is described by the de Broglie equation. So how do we tackle this problem? Well, they give us the mass, they give us the velocity, and we know Planck's constant. So perfect. We can then tackle this problem. So we go ahead and we plug in all the appropriate variables that correspond to this equation. And we know that the Planck's constant is 6.63 times 10 to the minus 34th joules times seconds divided by my mass, which is 1.00 kilogram, multiplied by 0.278 meters per second. Well, when we attack this problem, we have to kind of look at a number of things. Well, we have to first understand what are the units of a joule. So my units of a joule are equal to kilogram times meters squared divided by seconds squared. Okay, so let's go ahead and plug in our units for a joule up here so we can start canceling out the appropriate units. If you do not remember this, okay, you're going to have a lot of trouble trying to cancel out these units because they just won't cancel. Kilograms times meters squared times seconds squared, and then times second. This times second is just the additional component that's associated to the Planck's constant. So we have a second and second cancel, we have our other seconds cancel, we have 1 meter cancel, and we have our kilograms and kilograms cancel. It is very important to note that your units in this case, they have to be in kilograms. You cannot have units of grams. That also goes for your velocity. If they gave you units of, let's say they gave you kilometers per hour, you'd have to convert those units into the appropriate units in order to cancel out everything appropriately. So once we do this, we end up getting a wavelength that is equal to 2.38 times 10 to the minus 33 meters. Perfect. I have my units of meters. That's what my question asked for. That's how you tackle this type of problem. So it's very important to note what kind of equations you're using for each of these problems. Okay, if you're looking at a moving object, you want to make sure you're using the equation that relates to that to a moving object in order to determine the wavelength of it. And so when you are looking for the wavelength of a moving object, remember you're looking at the particle-like properties of that mass, and that's going to be and you're going to use the de Broglie equation in order to determine it.